Okay, cool. So before we get started, are there any questions about model theory people wanted to ask? We were in the establishing the basis that we knew that if you have a type of a big set, then there's a small subset over which it doesn't divide. We wanted to prove the same thing for forking. So we introduced this rank, d, q, phi, k, and we were in the process. So last time we were in the process of showing that if P is a partial type over A, well, okay, let me say it this way. If P is a partial type that forks over A, then for some delta and K, where delta is a finite set of formulas and K is a natural number, you have that d P delta K is strictly less than dp restricted to A delta K, assuming that dp delta K is finite for all delta and K. So if you know that you have a finite rank, like, you know, it's not infinite, then you know that when you fork, the rank drops for some delta and some K. Okay, so what is the idea? Okay, so last time we checked that at 0 it's true and at limits it's true. So it suffices to consider the case that what is it that we wanted to show? Well, okay, let's forget about this comment for a moment, and let's just consider the case. So it's okay. Here's what I mean. So, okay, we know if P forks over A, then, okay, P will prove some finite disjunction of formulas, I less than K, Ci, X, Ci, where each Ci, X, Ci divides over A. And it follows then that d of P delta K, for any delta in K, is going to be less than or equal to d, well, in fact, okay, it's equal to max. Well, no. Okay, I'm still sort of mixed up from the election. I think I'm all confused. So anyway, this is going to be less than or equal to dp restricted to A union Ci. So, oops. Okay, so I think the final thing I want to say is if I take the max over I less than K of these formulas with respect to delta and K, that if I replace P with P restricted to A and I add in each disjunct, that only can make the thing bigger because P itself will prove this disjunction. So certainly P is going to be less than or equal to this thing. So it suffices to show that if C xc divides over A, and P is a partial type, and let's say K divides over A, and P is a partial type over A, then dP union CXC Psi K is less than, strictly less than, dP Psi K. This is actually what we've reduced to showing. So why? Well, okay, so I know that P is the same thing as P union the disjunction of the formulas that fork. You know, this disjunction of formulas that forks. So if I replace P with P restricted to A together with this disjunction, I only make the rank bigger. So certainly this gives me like this inequality here. Now, we proved last time that if I want to compute the rank of a disjunction, that's the maximum of the ranks of the disjuncts. So I can replace P restricted to A together with this disjunction with a max of P together with each disjunct. Now, if each one of those things, P restricted to A together with a dividing formula, has rank smaller than P restricted to A, then I'm done, because certainly the max is too small. So this is what we've reduced to showing. Now, we know that if a type implies a type, then the type that implies the type has to have rank less than or equal to the type it implies. So if not, then P union Psi XC CK equals this, because it's a type that implies more. So if it's not strictly smaller, then they're equal, because the other inequality is always there. And so let Ci, I less than omega, be an A indiscernible sequence with C0 equals C, witnessing that Cx Ci, I less than omega, is K inconsistent. Then it follows that dP union Cx Ci Ck is equal to alpha for all I less than omega by invariance of the rank. So it follows that dP Ck is at least alpha plus 1, a contradiction. So if they're both equal to alpha, then this is also equal to alpha, but that would force that this would be equal to alpha plus 1, and that's a contradiction. So this is actually all we need. Now, okay, so that says that if you fork, then the rank drops. Now, what we want to do next is we just want to make the following observation. So, and this one is very easy. So if, well, in fact, let me say it this way. So if K is less than omega and phi xy is a formula, then d p phi k is at least n, if and only if the following is consistent. Okay, so So we're going to have a type in the following variables. So it's going to be x eta y nu, as eta ranges over omega to the n. So these are paths through the tree omega to less than or equal to n, and nu ranges over omega to the less than or equal to n, which says, okay, so one, it'll be the union over all eta in omega to the n, p x eta. So it says that every x variable realizes the type p. Two, it will say that paths are consistent. So for every eta in omega to the n, we have that phi x eta y eta up to I for I less than or equal to n is consistent. So, okay, maybe the better way of writing that is we have the conjunction over all I less than or equal to n of these formulas. So this goes in our type. So the way we would write that, I guess, is like this. And so this says paths are consistent. And then the third one will say that children of a common node are k inconsistent. So how do you say that? You say, okay, so whenever I take a nu, which is in omega to the less than n, so it's not at the top, then it's not the case that there exists a realization for all I in, let's call it W. So W will be an element of omega to the k, so a k element subset, which says phi x y nu concatenated with I. Okay, so what does that say? That says if I take nu and I look at k of its successors at the next level, then using those as parameters, I can't simultaneously realize all of them. So that says that children of a common node are k inconsistent. Okay, so we only have to prove this for the natural numbers. Let's think about why this is true. So proof sketch. Okay, so for n equals 0, what do you have to say? You just need p to be consistent. So if, for p to be consistent, it's clear that these things say nothing. So this condition here says nothing because the elements of, I mean, there are no elements of omega to the less than 0. That's not a set. So we consider this a trivial condition, and I guess maybe we want to say less than, strictly less than n in this case. No, I don't think so. Okay. It's a bit funny because it seems like this condition requires that some instance of phi be consistent with your type. Well, okay. So if we want, we could just say n plus 1, and then it's certainly true. So for n equals 0, there's nothing to show. So anyway, let me give the proof sketch. So the point is up to some change of n, I think it'll be fine. But okay, you have some type which is consistent. That means it has rank at least 0. Suppose it had rank at least 1, then that means you can break up realizations of your type into instances of phi, each of which are k plus 1 inconsistent and consistent themselves. Now, if you could do it twice, then that means you could further break up. Right? And so on and so forth. So I'm a little worried about this condition, number 2, which says that paths are consistent. But if we do this implication, then it's certainly true. And okay, so the consequence that we care about is if t is simple, then dx equals x, phi k is finite. That's supposed to be an omega. Is finite for all phi and k. Why? Otherwise, by the above, we find that phi has k tp. So if you had some formula which had the property that dx equals x had infinite rank, then for arbitrarily large n, you could build a tree of height n such that paths were consistent and children of a common node were k inconsistent. From that, it would follow that by compactness, you could build an infinite tree, and that would give you an instance of ktp, and that would mean that you're not simple. So simplicity implies that these ranks are all finite, and in particular, it follows that dp phi k is less than delta for all p. By monotonicity, because if it's true for x equals x, then it's true for everything else, and also holds for all finite delta. Okay, p finite delta p and k, because finite delta can be coded by a single formula. If you haven't seen this, then it's a good exercise to think through why. So if you have a finite set of formulas, then there's some other formula, assuming that your language has 2 constants, that you can use to code every instance of finite limiting formulas in terms of the single formula. So if you have a type, a partial type in delta, where delta is a finite set, then there's some other formula and a partial type in that formula which is equivalent to it. And okay, it's a nice game to play, to try to code a finite set of formulas into a single formula. So I won't spoil the surprise, but it's something that you can definitely do. And so because we know it for every single formula, then it follows that we know it for every finite set. So in fact, that will be equivalent to simplicity. But now we have a consequence. So important consequence. So if t is simple, there is no type p over a and chain of sets ai I less than the cardinality of t plus, such that p restricted to, well, we can just say p forks over ai for all I less than t plus. Okay, so why does this follow? Well, we know that if p forks cardinality of t plus many times, then it does so with respect to the same disjunction of formulas which divide with respect to the same k's cofinally often. So so first off, how many disjuncts are there? There are at most the number of formulas in the language. So if I fork t plus many times, then one of those disjuncts has to occur cofinally often, meaning t plus many times. Now, t plus is an uncountable cardinal. So each one of these finite disjunctions will be a disjunction of formulas that divide. Each one of those formulas k divides for some k. So that finite collection of natural numbers, or it suffices to think about the max of them, that is an uncountable collection of natural numbers. There has to be one natural number that occurs cofinally often. So we'll call that k. K will be the max of the k's such that the formulas in this disjunction k divide. So we can find some natural number that works that way. So then it follows that, okay, if I look at the D rank of P, delta K, this has to be strictly less than, or okay, let's say it this way. I should have said it that, okay, let me say it this way, PAI plus 1. You can arrange it this way. This isn't really different. So what we know is that P AI plus 1 okay, I apologize at how sloppy this is being. So anyway, so this is certainly true. So what we can say is let delta be the formulas in this disjunction, and k the max of the degree of inconsistency with respect to which they divide. So without loss of generality, replacing our sequence, we may assume that P restricted to AI plus 1 forks over AI via a disjunction of delta formulas that k divide over AI for all I less than t plus. So if I'm willing to replace my indexing sequence with a subsequence, I can assume that I always have the same disjunction. So the disjunction always comes from the same finite set, and the k with respect to those formulas divided is always fixed. Okay, so by taking the max of the formulas in the disjunction. So this is easy to do if your sequence is long enough. Okay, but then it follows that dp over ai plus 1 delta k has rank strictly smaller than dp over ai delta k. Why? Well, because you know that even if I just restricted delta to the dividing formula, whenever I have a dividing formula, the rank has to go down. That's what we proved above. Now, when I add more formulas, that doesn't change that fact, right? I mean, because we just needed to know that the dividing formula was in the delta. So certainly we have this rank going down, and that's a problem because we know that dp, which is the well, yeah, the dp delta. Well, okay. I mean, we can even say it more clearly. Okay, dp restricted to a0 delta k is finite by what I said above. So the rank is finite. That means it can only drop finitely many times from that point, right? If I continue on, so when I go from a0 to a1, I go down. When I go from a1 to a2, I go down. When I go from a2 to a3, I go down. I can only do that finitely many times before I run out of things. And so that's a contradiction. Okay, so this was very convoluted. I'll write it very clearly in notes in case people want to view that. But the structure of the argument is the following one, which is not so complicated. So we had two inputs. So the first one was it's easy to show by a kind of induction argument that if you know that the rank is at least n, where your delta is a fixed phi and the number is a fixed k, that forces you to have an approximation to the true property of height n, which means that if you are in a simple theory, then these ranks all have to be finite. Okay, so you know that the ranks are finite. Then using this ultrametric inequality and just the definition of rank, you can prove that when you fork, the rank has to go down. So as a consequence, if you have a forking chain of length t plus, then that meant that you had t plus many instances where the rank had to drop with respect to the same formula and the same k, and that contradicts the finiteness of the rank. Okay, so the upshot of all this is what we'll call a theorem. So this is local character. So T is simple if and only if for all types P in S of A, so for any set A, there is some A0 contained in A such that A0 has size at most T and P does not fork over A0. Okay, so one of the directions we already know. So one direction is the following. It says that if T is not simple, then we proved that there is a dividing chain of length T plus. So by the pigeonhole principle, well, okay, that's already enough. I mean, that's enough, right? So what do you get? You get, what does it mean to have a dividing chain? That means we have some sequence of formulas, phi I, x, yi, and ai, I less than t plus, such that okay, assuming you do your indexing correctly, this means that phi I x ai divides over a less than I. So what does that mean? We can define ai to be a less than I. And then it's clear that if we put P as a completion of phi I x ai, I less than t plus, then P divides, well, in fact, P restricted to ai plus 1 divides over ai. And hence it forks. So if you have a really long dividing chain, then you have a really long forking chain because dividing implies forking. And we did that before. How did this argument go? If you recall, we said, well, take a form, take something which witnesses the tree property. And then what you can do is from a witness to the tree property, you can make it S indiscernible. And of course, if you have a formula witnessing the tree property, then by compactness, you can stretch it to be as long as you want. So you can, of course, assume it's of height t plus. So once you have this S indiscernible witness to the tree property of height t plus, then you can just look at what happens on the all zeros path. Now, at any level, the formulas at that level, moving horizontally along the children of a common node, those are k inconsistent. But they're also inconsistent over the all zeros path below them. So if you take those elements of the all zeros path, that forms a dividing chain. That's what we did before. So this direction is easy, and it follows just from taking an S indiscernible witness of the tree property of height t plus. For the other direction, we say, okay, suppose not. Then you have some P in S of A. Then there exists some P in S of A. Well, you could say there exists an A and a P in S of A, such that P forks over every B contained in A with B sufficiently small. Okay, so what we'll do is we will inductively define a sequence AI, I less than T plus, such that, okay, each AI has size at most the cardinality of I, plus all of 0, because we'll take finite tuples, and P forks over well, we'll say P restricted to AI plus 1 forks over AI. Okay, so how do we do this? Well, we'll just put A0 is equal to the empty set. This is what we did last time, more or less. So we'll put A delta is equal to the union of alpha less than delta, A alpha, for delta limit. And given AI, by assumption, P forks over AI via some formula, let's call it phi xc. So then put AI plus 1 as equal to AI union C. So you fork, and that forking happens via a formula with some parameter. So put the parameter inside the set. So now P restricted to that set, AI plus 1, will certainly imply phi of x. C, and that means it forks. It implies the formula that forks. You just add enough parameters at each stage, some finitely many parameters at each stage, that let you see the forking that you need over the set that you had at the previous stage. Okay, then that gives a forking chain of length t plus, which contradicts simplicity. Using what we did before. So we proved that using this rank, that you can never have a sequence of sets and a type over the union such that at each successor stage you fork over the predecessor. And if you see that local character fails, then you can construct such a chain just by taking the empty set and then seeing that you fork over the empty set because it's too small. So then you add in those parameters and you fork over that set, and you add in more and more parameters and you build this really long chain. Okay, so is there? All right, so this is super key. And what local character says, just to repeat from what I said last time, is sort of that it's a compactness principle. It says that types always are determined by small subsets. So if I take a type, no matter how big the type is, maybe it uses all of 17 many parameters, there's a small subset over which it doesn't fork, meaning that I can think about this big type as a generic extension of a small type. And that type is really quite small. It's small in a universally bounded kind of way. Every type is a generic extension of some type over a set of size no bigger than the size of the language, which is a big deal. So this theorem is one of the most important things. And I will say that in most places where you learn about simplicity theory, this is in fact the definition of simplicity. They will say a theory is simple if every type over a complete set does not fork over some small subset, over a subset of size less than or equal to the size of the language. And then they have to prove that that's equivalent to the tree property. So you can make a choice. We did the original one because it's somehow going to make more sense going forward. That's going to be sort of the template of the way that the classes of theories that we care about are defined. They're defined in terms of tree properties. This is a class about model-theoretic tree properties after all. But you'll find in many places that this is taken as the definition, which makes sense in some ways because then you don't need to worry about types forking over their own domains or something. I mean, it just sort of follows. Okay, cool. So now what I want to prove is a super important result, which is called Kim's lemma. So let's recall the definition of a Morley sequence. So if A is a set of parameters, then a Morley sequence over A is an A indiscernible sequence AI, I less than omega, such that, and okay, I don't actually need to say omega. I have a bad habit of doing this. Let's say I in I, such that AI is forking independent over A with all of its predecessors for all I in I. And let's assume I is any infinite linear order. Okay, so you have an indiscernible, but it's like one of these like space filling indiscernible sequences. It's as generic as you could possibly make it. So if I take the I thing, it's free from everything that came before. All right, so we talked about this a little bit ago, but I think we've all slept since then. So it's good to remind ourselves. So now the theorem will be Kim's lemma. This says, suppose T is simple. then phi of x a divides over a if and only if for all Morley sequences I, which is ai I less than omega, with, so I should say over a, with a0 equals a, phi x ai I less than omega is inconsistent. Okay, so let's try to prove this now. All right, so first thing to observe and this is going to be a place where I'm going to brush something under the rug. So, I mean, I'm going to use something as a black box, and I'm just going to say that you can look it up because to prove it would actually take us pretty far from what we care about in this class. But there's something called the Erdos-Rado theorem. Which is like Ramsey's theorem, but for larger cardinals. So what that will say is if I want to color with infinitely many colors, then I can make my set really, really big and then still extract something homogeneous. So there's an old theorem due to Morley, in fact, which uses the Erdos-Rado theorem, which says, implies, so its model-theoretic application will say that given a set A of parameters, there is a cardinal kappa such that if ai I less than kappa is a sequence of same length tuples, there is some bi I less than omega, which is a indiscernible based on ai I less than omega over a, i.e. If, let's say, I0 is less than I1 is less than dot 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 is less than I n minus 1, then there is, let's say, less than, and there is J0 less than J1 less than dot 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 less than J n minus 1 less than kappa. So that's, if I look at the BI bars, these have the same type over A as the AJ bars. Okay, so what's going on here? Well, recall that when we were talking about the modeling property, we had this notion of being locally based. And what did it mean to be locally based? It said that whenever some formula was true of, like an increasing in tuple, for example, in the case of a indiscernible sequence, there had to be some other increasing in tuple from the original sequence, such that the thing it indexed satisfied the same formula. Now, there are too many types for you to apply Ramsey's theorem and get that anytime you realize a type, you have to have something in the original sequence which realizes the same type. It's very easy to see this, in fact. I mean, like if you take first order theory, which has countably many disjoint predicates, like P1, P2, P3, P4, you can of course take an indiscernible sequence where the first, not an indiscernible sequence, sorry. You could take a sequence such that the first element is in the first predicate, and the second element is in the second predicate, and the third element is in the third predicate, and so on and so forth. Now, an indiscernible sequence locally based on that sequence will obviously not be in any of the predicates. So in particular, there's no element in the original sequence that realizes a type realized by the indiscernibles. Because every one of the elements in the indiscernible sequence will, part of their type will say the predicate holds of me, and that can't be true of anything in the indiscernible sequence. The problem is just that the sequence is too short. So if you made it really long, much longer than the size of the language, then of course, if anyone was in the predicate, then many would have to be, or I mean, either you have many in the predicate or many outside, and so then it's possible. So that this tells you that if you make your sequence quite long, then Erdos-Rado, in the place of Ramsey's theorem, will let you not just realize formulas, but also realize types. And that's an important upgrade. So using this, we may construct a Morley sequence as follows. So given A, we know A is independent with A over A. Why? Well, because local character tells us that there's a subset of A over which the type of A over capital A does not fork. But that means that it can't fork over A itself because you had base monotonicity, right? Like if you don't fork over a small subset, then you don't fork over a bigger subset. That's what base monotonicity said. So in particular, no element forks over its own domain. No type forks over its own domain. So with this we have, then, so we'll put A0 as equal to A. Then by induction, we choose AI, which has the same type as A over A, with AI independent over A with A less than I by extension. And extension tells you can do this. So if I've constructed some things at a certain stage, then I can freely extend my type from A to A together with the stuff I've constructed, realize that, then that'll be independent from everything before. Then we apply Erdos-Rado. So once we've constructed AI I less than kappa, for this kappa coming from Erdos-Rado, we apply Erdos-Rado. To get A prime I less than omega, which is based on AI, I less than omega, and A indiscernible. So basedness will imply, in particular, we know that A prime I is still independent over A prime less than I because they have the same type. This finite tuple has the same type as something that came from the original thing, so it also has to satisfy this. So this says that Morley sequences exist. Okay, now that implies, in particular, that 2 implies 1. If you know that you divide with respect to every Morley sequence, and there is a Morley sequence, then in particular you divide. So what we'll do next time, in the first 5 minutes, because it really is like a super quick proof from what we've done so far, is we will prove Kim's lemma, and then we'll start moving in on the independence theorem on Monday. And I think that should probably take 2 days. So I think we'll probably do the independence theorem Monday and Wednesday, and then we will move on to in TP2. Okay, are there any questions?
I have a question actually.
Yeah.
So there's a different definition of Morley sequence that's sometimes used outside of the context of simple theories, where it's like you have an A invariant global type, and a Morley sequence
Yeah.
is just whenever you realize. See, so I'm pretty sure, right? In simple theories, those are equivalent. Are they still equivalent
No.
outside of simple theories?
They're
Okay.
not equivalents in simple theory. So
Oh, they're not equivalent in simple theories.
no. And actually, this is an important point. So in simple theories, there are examples. In fact, there's a reduct of the random graph, although I don't remember it off the top of my head, where over the empty set you have no types over the empty set have global empty set invariant extensions.
Okay.
So you over every set in a simple theory you have Morley sequences because no type forks over its domain. So whichever set you take, you have Morley sequences in that type. But there are examples where you have no invariant extensions, and so you can't apply this definition. So they're just importantly different. Of course, you're right that in a simple theory, or in fact in any theory, types sequences which are Morley in the invariant sense are Morley in this sense. But this is a strictly broader class of sequence.
So how did that happen then? The terminology thing.
Well, okay, so the original Morley sequence those come from Morley's paper,
right?
Category and Power, and there, the idea was you take something of the same Morley rank. I mean, you just choose something of the same rank over the things you chose before, and then once it was sort of understood that okay, rank dropping is the way you see forking in extremely tame contexts, but even in context of infinite Morley rank, forking makes sense. Then the terminology got extended to talking about Morley sequences in this sense. But of course, because invariant types are like super generic, it is like this process, right? You choose a generic realization of everything you had before, and then you observe that it's indiscernible. So I guess like anything that's somehow constructed this way of choosing a realization which is somehow generic over everything that came before and then making it indiscernible, I guess is like in some sense a candidate for being called a Morley sequence.
Okay.
I mean, I don't know that there's anything deeper to say than that.
Okay. Thank you.
Yeah, are there any other questions?
Yes, Nick.
Yeah.
Hi. So is this rank we defined, D rank, is some kind of refinement of U rank, or what is the relation between these things?
I think they agree sometimes. I'm not 100% sure when they agree. I mean, they're definitely not the same. So in particular, in U rank, of course, you don't have this like formula parameter and a K parameter.
Yes, and it is forking and not dividing.
But I think but I think that, okay, so you could look at a version of D rank where you have, you replace K with omega and you replace delta with L. So then you're just looking at instances of dividing. And then I think they're basically the same. Because then it's sort of like foundation rank on the instances of dividing. But I'm not 100% sure on the exact comparison.
Okay.
Do you see what I mean when I say replace delta with L and replace K with omega?
I think so.
So yeah, so in that case, it seems like you almost just get you just basically I'm a bit worried that these aren't exactly.
Sorry, I couldn't hear you.
I don't know. I'll check it. There are these papers. Oh no, yeah, it seems my connection's bad. Anyway, what I was saying is just that it seems to me, without really thinking and checking, that if you look at D rank where you replace delta with the entire language and you replace K with omega, so you look at any instance of dividing, then this is almost exactly the definition of U rank. But I'm a bit nervous that they're different for some kind of subtle reason. So I can check.
It's still different between the forking and dividing.
Well, okay. Yeah, true, but it shouldn't matter that much, because if you divide, I mean, if you fork, then that happens with the disjunction, and then the rank of the rank of disjuncts, and you're right. Like maybe this introduces some subtleties into how this works, but oftentimes the ultrametric inequality sort of erases the difference between forking and dividing.
Yeah, so that's why I asked.
Or like if you
there's a
maybe these
significant
things are the
difference.
same. If you assume that you're simple. Yeah. Okay. Maybe the most responsible thing to say is that I'm not sure,
Okay.
and I can check. Yeah, because I don't know off the top of my head sort of the ways that they come apart. I'm not sure that they do.
Okay. Thanks.
Yeah, it's a natural thing to ask, because I mean, so D rank came first, and then U rank came later, and I don't remember off. Okay. Well, I'll remind you all that if you want, you're always welcome to come to office hours at 12:30 today. And we will quickly finish up Kim's lemma and do the independence theorem at the beginning of next week. So enjoy your weekend. Stay sane. Don't lose your mind looking at election results. And I will see you all bright and early Monday morning.